Exponential functions, section 21. We're in the 20s. 21 out of 32. We're nearly down to the tens left, y'all. It's amazing. So, learning objectives, evaluate exponential functions, including E, use compound interest formulas, graph exponential functions using transformations. So, yes, transformations coming back on the scene. So, exponentials, you have something like y equals 2x minus 3 plus 7 sort of deal. Or this is still saying like up 7. This says, actually, it says right 3, all that fun stuff. Okay, we'll talk about that later. So, what is an exponential function? For any real number x, an exponential function is a function of the form f of x equals b to the x, where b is any real number such that b is greater than 0 and b cannot be 1. So what's the deal with b not being 1? That's not really a deal. It just says that if my base is 1, if I have 1 to the x power, then it's just 1. It's just it's not like a math secret. It's just like 1 to any power, even if it's 1 to the 1 millionth. Well, 1 times itself a million times is still a million. Because keep in mind that exponentials, right, just says that like if I have 5 cubed, that is just 5 times 5 times 5. So over here, 5 to the x just says this is 5 times 5 times 5. How many times? All right, keep in mind, that's what we're keeping track of. Okay. Oh, well, here, I guess I should read. Determine if each equation represents an exponential function. So 5 to the x, yes, because I have a base 5 with my variable in the exponential. So notice whenever I have the variable in the exponential, that's an exponential function. Remember, these people did not get crazy when they started labeling these things, right? They're like, oh, inventing math is so tiring. What should we call it? Let's call it like we see it. Perfect. Wonderful. I'm here for it. Verse x to the fifth, where x to the fifth very specifically says this is x 5 times. 1, 2, 3, 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. Yeah, hopefully that makes sense. So the variable is the baseline. The variable is the baseline, opposed to A, where the variable is the exponential. So C, what is it? Exponential or not? What do you think? Yes, an exponent. Because where's the variable? Where's that variable? Exponential. Yay! It is in the exponential position. Yeah. Okay, so now base E. Base E gets a very special whole section named after Euler. Okay, it's actually said Euler. It's German. Don't say Euler, it's Euler. I mean, if you said it, I would like mumble under my breath, be like Euler. But it's German, so it's got a weird spelling. It's named after the man who found it, but E is used as a base for many real-world exponential models. E is approximately 2.718. Okay, let's go. We usually just go there. 2.718. A lot of times it is linked to like the golden ratio. Golden, I can spell sometimes. Ratio. That nautilus, I cannot spell that. That shell, right? That seashell with all of the little chambers. Okay, that gets bigger. And other things that are not coming to mind. Oh, well, financial, that's an I, if you believe it. What am I compounding? Like how money grows on its top of itself. So because it occurs in nature, okay, occurs in nature, we call it the natural base, right? It's naturally occurring, natural base. So hopefully that is intuitive for your brain. But yeah, so with that, in a couple of days, we will talk about the ln, stands for natural log. Fun fact, it is the inverse to e. Okay, so inverses undo each other, right? Inverse functions are very much so related to each other. So the natural base, its inverse is called the natural log because exponents and logs undo each other. They are inverses to each other, just like root x and x squared, right? Roots and squareds undo each other. Exponentials and logarithms are inverse functions of each other. But I digress. Example 2. Evaluate each function. Round answers to 4 decimal places as necessary. So find f of -3. This means that we're just popping in what? -3. So we have 2 times 5 to the -3. Well, you may not remember, and that's totally fine. That's why I'm here. That negatives replace. Okay, not replace as in like substitute, but like move. So let's put it that way. Negative exponentials move position. So over here, cobweb information. Bloop, 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 bloop. Bloop. A to the -x is equal to 1 over a to the x. Just like if I had 1 over a to the -x, this is a to the +x. It repositions from denominator to numerator or numerator to denominator. So now, with that in mind, this is 2 over 5 cubed is 225, if memory serves. 5, let's just do 5 times the lazy man's way. 125, there we go. I knew 225 felt too long, too big. Yeah, so that's 2 over 125. It says to round, so 2 divided by 125, 0.016. Okay, you pause the video and try B and C. Come back when you're ready. Did you pause it? Did you pause it? Pause it. Really, pause it, try. Okay, all right, let's see. So this is just e squared, right? Because we're putting the 2 for the x. E squared, grab your handy dandy, clear this out. Above the log ln button is e to the, so e squared. Roughly 7 point, I lost it, 389. So in f of -1, change colors. This is -4 to the 2 times -1 plus 4. This is -4 to the, let's see, -2 plus 4, which is -4 to the 2 squared. So note, this says -4 squared. Does not say -4 squared. Do y'all see that difference? So let me show you what I'm trying to show you. -4 squared, -16 versus -4 squared, +16. So really you can shoot yourself in the foot if you're not paying attention to that negative placement. So please do not keep your feet, safe. Keep your feet safe. Oh, changed colors on accident. So sorry. Maybe not. Who knows? Anyways, color -16. So compound interest. Let me just check something really fast. Yeah, okay, sorry. I couldn't remember. Let me give you some more cobwebby rules. Keep in mind, We'll add them over here. Excuse me. So a to the x times a to the y is a to the x plus y. A to the x over a to the y is equal to a to the x minus y. A power to a power, we multiply. This is technically prerequisite knowledge, but I mean, for some of us, like prereq knowledge is a joke, which is fine because it could have been years. Math is not riding a bike. You lose it, you don't do it, you lose it. Let me put it that way. It's not a muscle memory. It is very much so something you have to keep at the forefront. So that's why we do this. Another thing we've talked about, but I want to touch on, remember that if I have a to the x over y as a fraction, that is the y root of a to the x. So this is where things can get tricky. You're like, well, it's not tricky already? No, I mean, well, I don't know. Yes. So remember that negative exponents bring in fractions. Fractional exponents bring in roots. Fun. Right? So just one thing that always I would like go back on, like I know to be true, is that root x is equal to x to the 1/2. Okay, if you can keep this in your mind straight, you should be on a solid path to help you move forward. So just keep that in mind again. Negative exponents move fractional position. Fractional exponents can bring in roots. Okay, so now here's compound interest. This is compound interest over a period, say like 5 years, 2 years, 6 months, whatever. A is equal to the accumulated amount. Accumulated amount. P is equal to the principal or the original amount, because principal is still pretty jargony. R is the rate. Oops, sorry. The rat. Who knows what I just wrote? R is equal to the rate as a decimal specifically. And T is time specifically in years, unless otherwise noted within the problem. Okay, so default setting, years. Then N is the number of compounds per period. Okay, number of compounds per period. Oops, except I swear I can write. All right. So you're going to know what your N number is based on, whoops, thought I was a highlighter. Based on what word is in the word sentence. So annually is 1. Semi-annually is 2. If anyone of y'all like sales like I do, semi-annually, a lot of companies have semi-annual sales, right? Like July and December, right? Twice a year. Quarterly, 4, right? 4 quarters make $1. Monthly, 12. What's weekly? 52. What's daily? 365. Although it is worth noting, if you're going into like business school, I think technically they actually use 360. Just, food for thought. So if you're talking to your friend and they're doing like econ homework and they're like, it's 360, bro. Be like, oh, okay. Well, your book just uses 365 for just like common knowledge sake. Just note. So you sound like you know what you're talking about if it happens to come up in your everyday life. Okay, but again, how do you know what N to use? It'll tell you in the word problem. Like weekly here just caught my eye in example 3. So I know that would say, oh, okay, weekly. N is equal to 52 because there's 52 weeks in a year. All right, so this is all to say, like, who cares? Well, let's talk about it, why we care in examples. An initial investment of $100,000 at 12% interest is compounded weekly. What will the investment be worth in 5 years? Okay, so when I'm starting out, I like to get all my ducks in a row. I need an A, a P, an R, an N, and a T. Those are all my variables that I need to plug in. I know that I have, let's go with, that's too dark. That's too light. Let's go with orange. An initial investment. So initial, right? That's AKA original of 100,000. I have that R is 12% interest, but we want that as a decimal. So that's 0.12. N, we already talked about, is weekly, 52. And then time, 5 years. So T is 5. Whoops. Now, I'm just going to appropriately slap all these numbers in to the equation above. Okay, plug and chug. Do not overthink it, which I know is hard, is easier said than done. But really and truly, just plug the numbers in where the formula above tells you to place them. So that is A equals 100,000 times 1 plus 0.12 over 52, all to the 52 times 5. Then you're just going to grab your handy dandy calculator and you're going to pop that in. So 100,000. Let me make sure I have enough zeros times 1 plus. And you can do the fancy division sign, but I also want to show you that this way also totally fine. 52 times, what was it, 5? There we go. Okay, and to have that like old school fraction, totally fine. Enter. All right. So 18208597. 1820. I already forgot. 1820. I messed it up, huh? 182085. 97. There we go. So we are, how much richer are we? We are $82,085.97 richer. Not too shabby. But hopefully that was okay. So you try 4 on your own. Try 4 on your own. Seriously, pause the video. Please try it. Pop it into your calculator because students struggle with, like, they're fine getting the equation, like getting the equation, like students generally are fine with, like popping it in. They're like, okay, see where that happens. I see over and over again students struggle with the calculator portion. So please practice with the calculator you're going to use for the test the best you can. Okay, please, please, please practice with your calculator because too many students miss points because they just didn't know how to use the technology, and I hate that for you. Okay, play when you're ready. Pause and then play when you're ready. Okie dokie. So again, all my ducks lined up. So I need an A. How much should be invested in an account? That pays 3% interest. Okay, so that's 0.03. How much should be invested? That sounds like a question mark for what's the original amount? Interest that compounds monthly. Okay, so that is 12 after 10 years. 10 years. So that it will have 4,500. So that is my A. Again, just Clap it in. So 4,500 is equal to P times 1 plus 0.03 over 12 to the 12 times 10. Okay, so I want you to recognize that this says 4,500 equals P times blah, 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 blah. So again, this is P times blah, 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 blah. What undoes times? Division. So all I want you to do is take 4,500 and divide by the blah, blah, blah. The 1 plus 0.03 over 12 to the 12 times 10. If you want to say, 120, go nuts. Now, this is what we're popping in. Figure it out. So I'll go fancy. Alpha y equals fancy fraction 4,500 over parenthesis 1 plus fancy fraction alpha y equals 1.03 over 12. And then, yep, close my parentheses. Oh, I double parentheses. That's fine. Raised to the 120, 12 times 10, right? Perfect. 333,493. 333,493. Okay. So we should deposit 3,334.93 into an account today so that in 10 years, oh boy, we can get like less than $200. That is because 3% interest is not a ton and compounding monthly is not a lot. Again, because the difference in 12% and 12% and a weekly compound. If it's your money, like if this is your savings account, you want high interest, high compounds. If you're borrowing the money and it's like a loan, you want low interest, low compounds, right? So I would want no interest is ideal, right? But yeah, 3% interest for a loan is good. And then you want like minimal compounds. Like I want that annual compound, right? The less, the better. But how'd you do? Did the division throw you for a loop? Yeah, that's okay. If not, yay. But if it did, it's okay. I tossed you into a bit of a deep end. But maybe after you saw it, hopefully it's better. So now, what if it's compound continuous? What if we like just don't stop compounding? Right? We think of like bacteria growth or population increase, right? Women don't get together and it's like, okay, we're only having babies on the first of every month, right? No, like it just happens when it happens. So what if, you're just constantly compounding? Then we get what we lovingly refer to as PERT. So again, like I said, there's that Euler's number because it is, has financial background. Like he came up with it from working in like finance problems. So PERT is definitely something you'd want on your note card. And then same with compound interest. Okay, so note card. Okay, unless you can just remember it between now and the next 3 weeks, note card. Make a note that you definitely want this on there. You need these equations. Okay, so a person wants to invest money. Person wants to invest $100,000 at 12% interest per year compounded continuously. What will be the value of investment in 5 years? Comparing the answer with the example in 3, which is the better investment? Okay, so as I said, I like my ducks lined up. So A is what we're looking for. We're investing the 10,000. R is the 0.12. Oh, N is the compound. We don't need that one, skirts. And T is 5. So we're just going to toss it in. A equals 100,000. E to the 0.12 times 5. Grab your calculator. 100,000, 1, 2, 3, e to the, so that is second over your ln, 0.12 times 5. So A is approximately, come back here, 182,211. And I think it was 88 cents. Yeah, yes, no, maybe. Oh, come back here. Yes. Okay. So now we're comparing $182,211.88 to what we got in 3, which was $182,085.97. So this one is the better option, right? Like I said, the higher the compound, chef's kiss. It's what you want. If you can get that compound continuous, awesome. I mean, you'll never get it. Banks know this. They don't want to just hand free money out, unfortunately. But yeah, you want high compounds. High, as high as you can get. That's what you want. If it's your money, if you have to pay it back, no thanks. Low compounds. Okay, so now example 6: a car purchased for 25,000 depreciates, right? Depreciates, right, to go lower in value continuously at 8% per year, sometimes said per annum. What will be the value of the car in 10 years? Okay. So, do we expect the output to be greater than or less than 25,000? Oh, less than. Good job. I just know that you said less than. So again, all my ducks rode up. We don't need N because that is E. So A is what we're looking for. Because it says what will, right? Will meaning in the future. P, $25,000. R, 0.08 because we want the decimal. Remember percent to decimal? Let's see, actually. If you forget how to go from decimal to percent, think Dr. Pepper. Percent to decimal. You move the decimal to the left twice. If you're going decimal to percent, you move the decimal to the right twice. Okay, and then that's 10 years. Whoops, wrong color. So A is equal to 25,000 times, oops, E to the Now here's the kicker, negative 0.08. I need a negative because I am depreciating, right, to go down. So I need my rate negative. Okay. And then times 10. So we're just going to grab the calculator, slap this in. 25,000, 2, 3, times E raised to the negative 0.08 times 10. That is 1123.3. And 23.3. And what was the cents? 22. So in 10 years, the value of the car is $11,233.22. I think that's pretty good. 10 years later, that's not shabby at all. I mean, not the best, but not terrible. Okay. All right. So I will hold off on graphs of this until we meet on Monday or next class because we're at 49 minutes. I'll stop the video. Bye. Have a great day.